Hey everyone, welcome back.
Glad to be here.
So today we are getting into something pretty high stakes. Imagine hitting upgrade on your company's massive production
Oh,
database.
yeah. That is always a tense moment.
Right. The progress bar loads, the system reboots, and for a split second, everything looks green.
And then the panic sets in.
Exactly. Suddenly, half of your critical customer queries start failing silently. The I/O latency spikes to just this unrecognizable level, and your phone starts ringing.
The dreaded DBA phone call.
Yeah, the one you never want to get. So today we have a very specific mission. We are doing a professional DBA to DBA deep dive into a comprehensive MySQL major version upgrade checklist.
It's essentially a survival guide for your database.
It really is, and I want to acknowledge right at the top, this blueprint comes directly to us from kedar.nitty-witty.com. We are sticking strictly to their methodology today.
Which is a meticulously structured document. I mean, if you are managing production databases at scale, you already know that a major version upgrade is not just, clicking a button in a GUI and hoping for the best.
Definitely not. It requires a really rigorous methodology.
Right. Our goal today is to walk you through this precise, experience-driven checklist from the initial isolated testing all the way to the cutover.
And the potential rollback, right. Can't forget that part.
Exactly. And we'll be focusing heavily on the underlying mechanics of why these specific steps are required. No fluff.
No fluff at all, just the steps and the strict reasoning behind them. Usually when you hear about IT upgrades in passing, there's this temptation to just spin up a new server, dump the data, and point the app at it.
Which is a recipe for disaster.
Yeah. But when you look at this blueprint, it treats the upgrade much more like a controlled scientific lab experiment.
It really does.
Starting right out of the gate with phase 1, which is upgrade testing, the checklist dictates a very specific topology. You need to provision 2 identical test servers.
Right. And they don't necessarily have to be production-like resources unless you were doing heavy load testing later. But you set up the current MySQL version on both.
So let's call them test MySQL 1 and test MySQL 2.
Perfect. So you establish a control group. That is the fundamental principle here. You restore your production data back up to both of those instances in a replicated environment.
Okay, so map that topology out for me.
Sure. So your topology looks like this. You have your production MySQL server, and replicating from that is test MySQL 1, which is on your current older version, and set strictly to read-only.
Got it.
Then replicating from test MySQL 1 is test MySQL 2, also on the current version, and also read-only.
Okay, so test MySQL 1 is our frozen control group. It stays exactly as it is.
Right.
But test MySQL 2 becomes our test subject. This is where we introduce the first major tool mentioned in the blueprint, which is the MySQL upgrade checker.
The central tool.
The checklist specifies installing MySQL shell, specifically on that test environment, test MySQL-2, to run the check for server upgrade function against the production database.
Yeah, and the logical reason here is proactive isolation at the syntax and configuration level.
So finding the bugs before they happen.
Precisely. You are running a diagnostic utility that scans the dictionary of your database before you ever touch the binaries.
Wow.
It is hunting for, deprecated features, incompatible authentication plugins, syntax clashes.
So instead of waiting for a fatal error to just crash the binary upgrade process halfway through, you're parsing the system ahead of time to find out if, say, a legacy authentication method is going to lock out all your application users on the new version.
Exactly that. If you don't document and resolve these notices now, they become fatal blockers later.
Makes total sense.
So once you have that list of necessary fixes, the checklist instructs you to implement those learnings into test MySQL-2. But this is where the methodology demands a very specific action.
Oh, this is the part about replication, right?
Yes. Before you actually upgrade the MySQL version on server 2 to your target version, you must intentionally disconnect replication between the 2 test servers.
Because if data is constantly flowing in and changing the start of the system,
you can't accurately isolate whether a performance degradation is due to your configuration changes or just a sudden spike in complex replication events.
that makes a lot of sense.
Yeah.
You are basically building your instruction manual in a vacuum so you know exactly what variables you altered.
Exactly.
Which brings us to the performance testing phase using a tool called PIST upgrade. Now, the blueprint requires you to collect slow query logs from the production MySQL server.
This is a massive step.
It is, because it specifies collecting at least 24 hours of logs. Honestly, 24 hours of slow query logs on a high-traffic production box is a massive amount of data.
Oh, absolutely.
You're potentially talking about gigabytes of raw queries. Parsing that through a test environment sounds like a heavy storage and compute nightmare. Is 24 hours just an arbitrary number, or what does that specific time frame achieve?
It justifies it through the reality of the business cycle. I mean, a standard business day is not monolithic.
Sure.
You have morning reporting queries that hit heavy aggregation tables, afternoon transactional peaks with millions of tiny inserts.
Right, the workloads change entirely.
Exactly. And then you have midnight batch jobs that perform massive data purges or index rebuilds. If you only capture 4 hours of logs during the afternoon peak, you might completely miss the heavy analytical queries that run overnight.
And then your database falls over at 2 a.m.
Precisely. You need the full 24-hour cycle to guarantee you are testing the complete holistic workload profile of your application against the new database engine.
I get it. So you take that massive, comprehensive 24-hour log, and the checklist outlines a two-step process for Pete upgrade.
Right.
First, you execute the tool for read-only testing. You replay those captured queries against both your control server and your newly upgraded test server to see how they handle the exact same read requests.
That's step one.
And then step 2, you enable read-write on both instances and execute Pete upgrade for read-write data load, actively modifying data to compare the results.
Yeah, and you are looking for very specific deviations in the output of this tool.
Like what?
Well, the blueprint highlights 4 critical issues to log for your fixture list. First, execution time differences.
This is where DBAs usually get caught off guard, right?
Sure.
A query that historically took like 50 milliseconds suddenly takes 4 seconds on the new major version.
Yeah, and that's often because of changes to the optimizer cost model.
Oh, interesting.
The new database engine might evaluate the statistics differently and decide that a full table scan is somehow, cheaper than using the index it relied on for the last 3 years.
Which is terrifying.
It is. You have to catch those execution plan regressions now. Second, you log result set differences. Does the exact same query return differently ordered data on the new version because a default sorting behavior changed?
Right.
Third, execution errors.
Yeah.
Queries that just outright fail.
And fourth, reserved keywords. That's a classic trap. Someone named a column rank or system 5 years ago, and in the new major version, that word is suddenly a reserved system function.
Exactly. You catch it all here. And to wrap up phase 1, the checklist mandates application compatibility testing.
Because the database doesn't exist in a vacuum.
Right. The application itself must be pointed at the newly upgraded test MySQL L2 to document any application-level issues or driver incompatibilities. This directly results in the creation of an application update plan.
Okay, so phase 1 was all about finding the problems. We've essentially built this massive, terrifying list of everything that's going to break. Very much. But a list of problems isn't a strategy. How do we actually inject these fixes into a live runway without disrupting the current production traffic? That brings us to phase 2, which is upgrade preparation.
Phase 2 begins with issue resolution. You're actively applying the fixes identified during the check for server upgrade phase and the TEPT upgrade testing.
So putting out the fires we just found.
Exactly. This involves implementing the specific database-level config changes required for compatibility. The checklist explicitly calls out authentication changes, which is vital.
Why is that one so critical?
Because if the new version uses a stronger default password hashing algorithm, your legacy application drivers might simply refuse to connect.
Oh, wow. Yeah, and you validate those fixes directly with the app team, right? You can't proceed if they haven't signed off that the new authentication method works with their connection pools.
Right. You need that official... Go ahead.
Assuming we have that green light, we move to infrastructure and cutover preparation. This is where we build the candidate environment.
The candidate strategy.
Yeah, the blueprint says to provision production-grade servers for the new environment, or utilize the existing test servers if they actually meet production specs. Let's call them candidate prod 1 and candidate prod 2.
Now, the sequence the checklist requires here is the absolute core of the risk mitigation strategy. You do not just install the target new version of MySQL on these new servers.
Wait, you don't?
No. You set up the candidate servers with the current older version first. You restore the data, and you set up change replication from production.
Okay, so production replicates to candidate prod 1, which replicates to candidate prod 2, all running the old version.
Exactly.
It's basically a dress rehearsal. You install the old version just to immediately upgrade it because you are validating the procedure, not just the final destination.
Exactly. You then perform the upgrades to the target version on those candidate servers using the exact meticulous learnings, the specific my.cnf changes, the exact query fixes that you documented during phase 1.
Because you are building an exact replica of what production will be.
Right. By applying the documented steps to a live replicating environment, you prove that your instruction manual actually works under production-grade replication conditions without breaking the thread.
And because this candidate environment is literally destined to become the new production environment, the checklist explicitly requires you to configure and test your backup
Oh,
solutions.
absolutely.
You set up and validate your monitoring systems and critically test restoration from those backups in this candidate environment.
You can't assume your old backup scripts or your monitoring agents will parse the new dictionary tables or the new data directory structures flawlessly.
That makes total sense. You validate them here in the candidate runway before you ever route customer traffic to it.
Mhm.
So you document this new environment, finalize the cutover requirements with the application team, and phase 2 is complete.
Which means the runway is fully paved. We arrive at the critical execution phase. Phase 3, cutover.
Here we go.
You have a tested candidate environment replicating seamlessly from production. Now it is time to execute the switch.
But the pre-cutover activities are unforgiving, according to the checklist. You must verify replication is functioning properly with minimal lag and absolutely zero errors.
Zero errors is key.
Yeah, you ensure the latest full backups from the current production system are available and validated. You confirm all monitoring systems on the candidate side are fully functional, and you notify all stakeholders that the maintenance window is starting.
Only then do you move to cutover execution.
Okay, walk us through the exact sequence.
Step 1. Implement read-only mode on the current production database. Flipping to read-only is always that breath-holding moment because you're instantly rejecting client rights.
Right, so your application better have proper retry logic or graceful degradation built in for that specific window.
Exactly. It is the point of no return for the application's write availability. Step 2. Verify replication has fully caught up.
So no lag.
Absolute zero lag between the current production database and your candidate environment. Every single byte must be accounted for.
Got it. Step 3, disconnect replication from current production to the candidate MySQL production primary. I like to think of it like safely uncoupling a train car.
That's a good way to look at it.
You only pull the pin when you are absolutely sure the train has stopped completely, the brakes are on, and every single piece of transaction cargo has been safely transferred to the new car.
And you don't just uncouple the car. You make sure the new track is already fully built, tested, and structurally sound before you switch the rails.
Right.
Once uncoupled, the candidate environment stands completely alone as the new source of truth. Step 4. Update the connection strings and configuration in your application to point to this new candidate environment's writer instance.
Step 5. Enable read-write on the candidate MySQL production primary. Step 6. Start application traffic to the new database environment. We are live on the new major version.
But you don't walk away. Immediately, you perform validation tests against critical application functions. You aggressively monitor for errors or unexpected performance degradation.
This is the critical decision point, isn't it?
It is. Based on that immediate monitoring, the stakeholders make a definitive go or no-go decision for continuing with the upgrade.
Let's assume it's a go. The application is humming, queries are fast, CPU is stable. We move into post-cutover activities.
Right.
We continue to monitor application performance, error rates, and database performance metrics. We collect these metrics to compare them directly with the pre-upgrade baseline we established earlier to prove we haven't introduced silent latency.
Exactly.
You document any minor issues encountered, resolve them, and notify the stakeholders of a successful upgrade completion. But the checklist demands one crucial step that defines the final phase of this entire document. Keep the original environment available.
Yes. You do not tear down the old production server. It sits there, paused, holding the exact state of the data as it was the moment you flipped the read-only switch.
Which brings up the nightmare scenario. What if an hour later the application is just choking?
It happens.
The execution plans looked fine in testing, but live concurrent load from thousands of users is suddenly tanking the CPU on the new engine. We need that safety net. Which brings us to the final section of the blueprint, the rollback plan.
A professional upgrade methodology always assumes failure is an option. The rollback preparation starts with a critical technical check. You must check if reverse replication is a possible option.
Meaning, can you take the new data being written to the upgraded candidate server and replicate it backwards to the old original production server?
Exactly. And often between major versions, that is incredibly difficult or impossible because the new version might introduce entirely new data dictionary formats or redo log structures that the older version's replica thread simply cannot interpret.
Right, it just can't read the new language. So if reverse replication breaks or isn't possible, you essentially have an air gap.
You do.
The checklist mandates that you identify and note any manual actions needed for the rollback. Because if reverse replication fails, any data written to the new system during that hour of uptime might be permanently stranded if you revert to the old server.
And this ties directly into the business logic. The blueprint explicitly states you must establish the application's tolerance on possible data loss or delay in data restore.
So the business has to make a hard choice ahead of time.
They do. If things go sideways, do we keep the broken new system and try to fix it forward, or do we roll back and accept the loss of an hour of customer transactions?
Wow.
Therefore, you must define the precise triggers for a rollback decision. What specific metric, latency threshold, or error rate forces you to hit the undo button?
You establish exactly who has the decision-making authority to make that brutal call, and you prepare the rollback scripts and procedures well in advance.
Yes, preparation is everything here.
So if that designated authority looks at the tanking metrics and makes the no-go call, we move to rollback execution. It is essentially the cutover sequence in reverse.
Pretty much.
You update the application connection configuration to point back to the original production database. You return that original database from read-only back to read-write mode. You verify application functionality with the original database, effectively marooning the failed candidate environment.
You then notify the stakeholders of the rollback, provide an expected resolution timeline, and finally, you document the specific issues that triggered the rollback.
When you look at this whole blueprint, the rigid, systematic nature of it is incredible.
It really is.
We didn't just walk through an installation wizard. We started with isolated control group testing, parsed the dictionary for syntax clashes, ran gigabytes of slow query logs through piped upgrade to catch optimizer cost model changes.
Built a candidate environment just to rehearse the actual upgrade procedure.
Yeah. Right. Executed a zero-lag cutover sequence and defined precise business-level rollback triggers just in case. It is an absolute masterclass in risk mitigation.
It is. And if we look closely at the architecture of this checklist, it leaves us with a rather provocative reality about the future of our industry.
Oh, how so?
Well, as managed databases and AI take over routine administrative tasks, the mechanical act of upgrading is becoming highly automated. But this checklist proves that the ultimate success of an upgrade doesn't rely on the execution of the cutover itself.
Because that's just flipping a switch.
Exactly. True success relies on the meticulous human-driven documentation of every single config change and application incompatibility discovered during the lab experiment phase.
Combined with the deeply human business logic of defining data loss tolerance during a rollback.
Right. It makes you wonder, as automation increases, will this level of meticulous human-driven rollback planning become a lost art? Or will the stakes simply get higher because we forget how the underlying plumbing actually works?
That is the exact question every DBA needs to be asking themselves right now. Guessing is the one variable you can never allow in the experiment, no matter who or what is running the scripts. Thank you all for joining us on this DBA Deep Dive. We'll catch you on the next one.